I'm sorry. So first of all, I'd like to say thanks to the organizers to give me the opportunity of this talk, and also every hospitality in my stay in Korea. So today I will give a talk on isoparametric hypersurface geometry. This is a subject, my subject I've been studying for more than 10 years. So. And in Japan, I give the same talk several times already, so maybe some of you have already attended my talk again and again. Sorry. Oh, this is the same one. So my talk plan is as follows. So I'll give a brief introduction of isoparametric hypersurface theory. And then I'll mention my recent result on classification of the hypersurface. And then I'll give a new result, which is the expression of the defining polynomial in terms of the moment map of the spin action. And then finally, I give a summary and some related topics. So first, I give a definition, I give some background of isoparametric hypersurface theory. So this started in the early 19th in Italian geometers in the subject of geometric optics. So it deal the wavefronts which develops with time. And follows the Huygens principle. You know, all of you, I know, I think you know Huygens principle. So we study about the time developing surfaces following Huygens principle, or here I consider hypersurface case too. And in general, the isoparametric function is defined on a complete Riemannian manifold, but in this talk I mainly consider M bar as a sphere. So let's consider M bar the complete Riemannian manifold with Levi-Civita connection and the Laplacian. Then by definition, a class C2 function on M bar is an isoparametric function when f satisfies these two PDEs. And the first PDE means that the square norm of the gradient vector of f is a function of f itself. So here phi is a function on the range of this function, and this is real valued and of class C2. This condition geometrically means the following. So if we restrict to the level set of f, here f has constant value t0. So this left-hand side here takes constant value along the level set. So this means that each level set is parallel to each other. Where I say parallel, the two level sets are parallel, which means they are located in the same distance in the normal direction. So if we restrict on the level set, then this gradient vector has the same norm. So the next level set is constant distance from the original one. So all the level sets are mutually parallel. This is the meaning of this first equation. And also second equation says that the Laplacian of f is also a function of f itself. But we just assume this is a continuous function. What does it mean? This means along this level set, the mean curvature is constant. So Laplacian means mean curvature. So along this level set, the mean curvature is constant. So all the level set hypersurface has constant mean curvature. This is the meaning of this second equation. So if f satisfies these two conditions, then we call this function an isoparametric function. And a level set of f of the regular value of f is called isoparametric hypersurface. The example of easy case is as follows. So if we consider a square norm of the position vector of the Euclidean space, then the gradient vector of this function is, of course, 2 times x. So the square norm is 4 times f. And the Laplacian is 2n, this is constant. So this function satisfies these two conditions. So this is an isoparametric function. This is very easy function. And the level set are, of course, round spheres. They are isoparametric hypersurface in the Euclidean space. So Eric Cartan in 1930s give the fundamental fact on isoparametric hypersurfaces. So fundamental characterization in the case of space forms. So this space forms, Euclidean space, sphere, and hyperbolic space are very, very simple space. And they Cartan characterized such family of parallel hypersurfaces as follows. So these three conditions are equivalent. So the family of parallel hypersurfaces is a family of isoparametric hypersurface, which means that there exists a global function on this Riemannian manifold, and each MT is given as a level set if and only if all the hypersurfaces have constant mean curvature. And this is also if and only if one of M has MT has constant principal curvature. So if just one hypersurface here has constant principal curvatures, then all other hypersurfaces have constant mean curvature, and there exists a global function, isoparametric function, and this hypersurface is given by a level set of such isoparametric function. So this third condition is a local condition because the principal curvatures are local notion. However, it implies this global existence of isoparametric function. So this fact shown by Eric Cartan is very important and non-trivial. So the known examples of the isoparametric hypersurfaces in the space form is easy in case of hyperbolic and Euclidean case. So in Euclidean case, the isoparametric hypersurfaces are only a totally geodesic hyperplane or totally umbilic sphere, or the product of such a submanifold. And this is called a cylinder. And so only these three cases. And also in hyperbolic space, isoparametric hypersurfaces are given by equidistant hypersurfaces, including hollow spheres, or umbilic sphere, or the product of these two spaces. And there are none, no more examples exist. However, in the Euclidean sphere case, there are many homogeneous hypersurfaces in the sphere. And homogeneous hypersurfaces have constant principal curvature, of course. So they are examples of isoparametric hypersurfaces. And here there are more examples other than totally umbilic one and the product of two spheres. And surprisingly, there are more non-homogeneous examples in the sphere. So this was first shown by Ozeki and Takeuchi, and then generalized by Ferras, Kalkya, and Münzner. I will mention in detail later. So from now on, I restrict my argument to the case M bar is the sphere. In this case, Münzner gave a fundamental characterization of isoparametric hypersurfaces. For instance, we traditionally denote by G the number of distinct principal curvatures, and it takes value only 1, 2, 3, 4, and 6. Also, if we put the principal curvatures from the large one to the small one, then the corresponding multiplicities satisfy Mi is equal to Mi plus 2, the index modulo G. So this relation implies that when G is odd, for instance 3, then all the multiplicity coincide. And also there exists the so-called Cartan-Münzner polynomial in the one-dimensional higher Euclidean space in which sphere lies. And this is a homogeneous polynomial of degree equal to the number of distinct principal curvatures. And the two PDEs are given in this way in the extended case. So this means the Euclidean gradient of this polynomial, and the square norm satisfies this G to the power 2 and the norm of X to the power 2G minus G. Also the Laplacian, this is the Euclidean Laplacian of F, is satisfy this condition. So when, for instance, all the multiplicity is coincides, then the right-hand side becomes 0. So this polynomial becomes a harmonic polynomial. And then we restrict this large F to sphere. This gives an isoparametric function on the sphere. Vice versa. So if we start from an isoparametric function on sphere, we can extend it to a homogeneous polynomial of one-dimensional higher Euclidean space. And this function restricted to F takes value between -1 and 1, interval -1 and 1. So if we take the endpoint, so plus minus 1, then the level set becomes a lower dimensional regular submanifold, and they are minimal submanifold. We call them the focal submanifolds. Then the isoparametric hypersurfaces and the focal submanifolds sweep out the ambient sphere. So the ambient sphere has a singular foliation. And also the sphere is divided into two disk bundles, B plus and B minus, over M plus and M minus, focal submanifold. I will show this in the picture in next page, but the intersection of these two disk bundles is nothing but the isoparametric hypersurface. This is shown in this way. So the simplest case is when G equals 1. In this case, isoparametric hypersurfaces are hypersphere, just a hypersphere. And the two focal submanifold consist of 2 points, North Pole and South Pole. And if a wave starts from this point and develops in this way, then shrink in this way and collapse into the South Pole. So in this case, it is clear that this ambient sphere is divided into two disk bundles, B plus over M plus and B minus over M minus. This is the simplest case. And this any isoparametric hypersurface may be considered as this disk bundle, intersection of this disk bundle and this disk bundle. When G is equal to 2, then the two focal submanifolds are given by this totally geodesic subsphere and this totally geodesic subsphere. And if from each point of this focal submanifold, a wave start like this. Starting from this develop in this way at each point. So we have some here is M plus, and each point there exists maybe, yeah, okay. We have a wave which develops in this way. Then this family of sphere has envelope sphere here another sphere. And maybe it's difficult to write this. So this here is Sk minus 1 maybe, and this here is Sn minus k, and the product is the isoparametric hypersurfaces. So if this wave develops in this way, then this another envelope sphere becomes smaller and smaller and finally collapses into this focal submanifold. So this part is an isoparametric hypersurface, and it develops in this direction and in this direction and collapses to this another focal submanifold. So in this case, the disk bundle B plus is shown as a strip in this part, and another disk bundle over M minus is a strip in this part. Of course, this does not intersect because they are mutually orthogonal space. They belong to mutually orthogonal space, but you can't show in the picture. So you can suppose this is a B plus and this is a B minus. And similarly, when G equals 3 case, there are also two focal submanifolds here. This is a projective plane, and another focal submanifold is another projective plane. And also it develops the wave from each point of this focal submanifold, and then it collapses to another focal submanifold. This is a picture of isoparametric hypersurfaces. And when G equals 4, the focal submanifolds are expressed by two squares. And in G equals 6 case, focal submanifolds are two hexagons. And this circle means the normal geodesic. If we have here a point of isoparametric hypersurfaces, then this is the normal direction. And so this circle means normal geodesic. So in this picture, this is a normal geodesic at some point here, or between here there is a isoparametric hypersurface MT. So MT is parameterized by this interval. So MT, at each MT there is a same normal geodesic. So this is a rough picture of the isoparametric hypersurfaces. And the classification is almost done in sphere case 2 now. So of course, when G equals 1, this is hypersphere, and G equals 2, the product of small sphere, this is called Clifford hypersurface. And when G equals 3, this is called the Cartan hypersurface, which has been already found by Cartan and classified by Cartan. So this is given as a tubes over the standard embedding of the projective plane. And F its real complex quaternion or Cayley numbers. And according to F, we take this D, the dimension 3D, the D, it's just a multiplicity of the principal curvature given by 1, 2, 4, and 8. So this is called the Cartan hypersurfaces, and classification has been done, these 3 cases. Then I skip the 4 case I mentioned next. So I skip to the G equals 6 case. In this case, average gives a very topological complicated argument to obtain that all the multiplicity coincide, and this M takes only values 1 or 2. And in each case, we have a homogeneous examples, and they are very closely related to Cartan hypersurfaces. How is the relation? When M equals 1, this homogeneous hypersurface with 6 principal curvature has a fibration over S3 with fiber consisting of Cartan hypersurface, real Cartan hypersurface. So this is 3 dimension, this is 3 dimension, and this hypersurface is 6 dimension. Also, in the multiplicity 2 case, the homogeneous hypersurface with 6 principal curvature has fibration over S6 with fiber, the complex Cartan hypersurface. So the homogeneous example is easy to understand through this fibration structure. However, the problem is whether there are other examples or not in G equals 6 case. So the Dorfmeister and Neyer proved that when the multiplicity is 1, all homogeneous, all isoparametric hypersurfaces are homogeneous, must be homogeneous. They are given by this example as an SO4 orbit. And this is already 30 years ago. Dorfmeister and Neyer, almost 30 years ago, they proved it. However, the way of proof is very algebraic and not so easy to understand nor to extend it to the case of multiplicity 2. So I give a geometric proof, another proof, and in the same principle as this case, I could extend the proof to M equals 2 case. And so I got the result that the isoparametric hypersurfaces with 6 principal curvatures with multiplicity 2 must be homogeneous. This is given by the G2 orbit, like this. And the way of the proof it's just to show the equivalent relation, equivalent condition, which is called condition A. So I have already proved that isoparametric hypersurfaces with 6 principal curvatures are homogeneous if and only if condition A is satisfied. What is condition A? This is to say the shape operators of the focal submanifolds have kernel independent of the normal direction. So it is known that the shape operator of the focal submanifolds have a constant eigenvalue. However, the eigenspace changes with respect to the normal direction. So condition A says that zero eigenspace, kernel means zero eigenspace. Zero eigenspace does not change with respect to normal direction. This is condition A. However, to show this condition A is extremely difficult, especially for the case M equals 2. Why? One of the reasons is that when the multiplicity is 1, the principal vectors give a natural frame. So we have a standard frame consisting of principal vectors. However, when M is 2, the eigenspace, the curvature space is of dimension 2. So the frame rotates in this way. So we have no standard choice of a natural frame. So how to choose a natural frame? This is a big problem, and it took me several years to find a natural frame. Then with respect to a natural frame, we can express the shape operator of the focal submanifold. And this is a 10 by 10 matrix. And as I said before, this matrix, family of matrix has a constant eigenvalue. However, so we call it isospectral. However, the isospectral family has freedom of the orthogonal group of degree 10, because all of you know, if a matrix has eigenvalue, then of course such matrix has also the same eigenvalue. So in our case, this is 10. So the family of isospectral operator is of dimension 45. So we want to specify the kernel, but algebraic argument is useless to specify kernels. So we need a geometric argument. We need some symmetry or some analysis using the Fourier expansion of an S1 family of shape operators. And I also use Mathematica to compute this analysis. Anyway, finally, I could show that this hypersurface satisfies condition A. So in that case, all the components of the shape operators we can compute, and then we can show that they coincide with the homogeneous one. So applying the Bonnet's fundamental theorem on hypersurface, we obtain our classification theorem. So this is the story of G equals 6 case. And I will give some remark in higher codimensional case. In this case, the definition of isoparametric submanifold of the sphere, maybe this is not necessary that sphere. However, I restrict my talk to sphere. Is a submanifold with trivial normal bundle of which shape operator with respect to a parallel normal field has constant eigenvalues. So this is the definition of isoparametric submanifold given by Julian Tan. And this submanifold case has been classified by Torbergson independently by Olmos just when codimension is larger than 1. So hypersurface case is the most difficult. So codimension rather than 1 case are all homogeneous. This is shown by Torbergson by using the Titz building, and by Olmos by using the theory of normal holonomy. So this case is settled 20 years ago. However, 10 years, 20 years ago. However, the codimension 1 case, the hypersurface case, is left. And this is the most difficult case, and one of Yau's problem. However, up to now, the G equal 1, 2, 3, and 6 cases are all settled. So I move to the case G equal 4. The examples known up to now is classified in this way. So almost all the cases belong to the OT-FKM type. OT means Ozeki Takeuchi, and FKM means Ferras Kalkan Mitsuna. And these cases, as I said before, include non-homogeneous examples and homogeneous examples. And there are only two non-OTFKM type hypersurfaces with 4 principal curvatures. And in 2003, maybe, Cecil, Chi, and Jensen, and independently by Immanpool, these exhaust the isoparametric hypersurfaces with 4 principal curvatures, except for 4 cases. Then Koshin Chi studied between about 5 years, and he could settle 3 cases among 4 cases. So now just the remaining case is M1 is 7 and M2 is 8 case, just 1 case. Except for this case, the isoparametric hypersurfaces with 4 principal curvatures are classified and included in this table. Now, what is the OTFKM type hypersurface? This is constructed by using the Clifford algebra. So I will explain. The Clifford system is given as follows. So let's denote by ON the orthogonal group, and the small ON, it's Lie algebra. Then set of elements of the orthogonal transformation is called a Clifford system, if and only if this relation is satisfied. And here, if we put here minus sign, this is called Clifford algebra. However, we consider plus sign, and this case called Clifford system. But it is very easy to show that Clifford system corresponds in a one-to-one way to representation of Clifford algebra. This is very easy. Anyway, so Clifford system means representation of Clifford algebra. And this here is some integer m and l. And the pair is possible only in these cases, which was shown by Atiyah, Abbott, and Shapiro. And the modulo 8, this m and l relate in this way. And if we put L to be delta M as a function of M in this part, then when M is larger than 8, we have L is equal to 16 times of the corresponding M. Yes. So there is an infinite series of these pairs. And even the same for same M and L, there are non-equivalent Clifford systems exist. Now, with respect to the product, inner product of on the orthogonal this orthogonal group, we take such normalization 1 over 2L. 2L is the dimension of the space of which act Pi act. Then, if we take this normalized inner product, then P0 to Pm is an orthonormal basis of the space spanned by themselves. So P0 to Pm spans a space of symmetric orthogonal operators. Symmetric follows from this relation. If we put I equal to j, we have a relation which says orthogonal and symmetric. So it becomes a space of symmetric orthogonal operators. And P0 to Pm are also normal frames. Now, Ferras, Kalhan, and Münzner obtained the Kaltan-Münzner polynomial. This is the extended version of isoparametric function on the sphere. given in this way, in this simple polynomial. This is a polynomial consisting of this Clifford systems. So if we are given a Clifford system, then this polynomial of degree 4, this is degree 4, is a Cartan-Muntner polynomial. And when this L and M satisfied this condition, L minus M minus 1 is positive, then the restriction of this polynomial to just here is a isoparametric function. So the level set are isoparametric hypersurfaces. And because this is of degree 4, the number of principal curvature is 4. And multiplicities are given by M and L minus M minus 1. So this is a big discovery, I think. But in the background, there is a very geometrical argument given by Ozeki and Takeuchi. So this formula owes to Ozeki and Takeuchi, I think. And among these isoparametric hypersurfaces, there exist infinitely many non-homogeneous and also homogeneous examples of isoparametric hypersurfaces with 4 principal curvatures. Yeah, and then we want to have a spin action. So if we are given a Clifford system here, then the composition of Pi and Pj becomes skewed by the relation of this relation. Pi composed Pj becomes skewed. So it generates a Lie subalgebra isomorphic to OM plus 1. And this Lie subalgebra generates a Lie group, and it acts on this space, the original Euclidean space, as a spin action in this way. And Perras, Calher, and Muntner show that this spin action preserves the Cartan-Muntner polynomial. So along isoparametric hypersurfaces, this spin acts. But this is a small subgroup of this large subgroup. So the action is not transitive, of course, in general. But, however, we can express the Cartan-Muntner polynomial in terms of only this spin action. This is the goal of this talk. However, this action, spin action on 2L-dimensional Euclidean space, it has a symplectic structure because it is isomorphic to the complex vector space. However, this action is not symplectic. So we cannot apply directly moment map to this action. There are no moment map to this action. So we need some idea. It is a very simple idea to extend this action to the tangent space of R, just Euclidean space. So for each Euclidean space, the tangent space is isomorphic to the complex vector space. And this is a Kähler manifold. So we have a natural Kähler structure and Hermitian inner product. So we can define the two form in this way. This becomes a closed two form, and this becomes to be a symplectic form. So this has, of course, a symplectic structure, all of you know. And so we extend the isometry action on the Euclidean space to this tangent bundle from the left action naturally. Then we know that this extended action is Hamiltonian. So Hamiltonian action has moment map. And this moment map is a map from this tangent bundle to the dual of the Lie algebra of K. And the equation, the formula is very simple. And this is a very classical physics. So when n equals 3 case, all of you know this is a moment map of phase space. So just we apply this argument to this our spin action. And in our case, this PIPJ we denote by zeta ij is an orthonormal basis of this Lie algebra. So we express this moment map with respect to the orthonormal frame. Then we obtain this formula. This is also very simple. And we take the square norm with respect to the inner product I defined already. Then it is easy to see that the square norm is, of course, the sum of the square of this inner product. So now compare this term with this term. This appears as the second term of Cartan-Münzner polynomial given by Ferras, Karcher, and Münzner. So compare these two. Then we recognize that if we choose this y in the this y in a suitable way, then this coincide. To find this y is trial and error. I make some trial and error and found that if we choose this tangent vector field in this way, so when P0x is orthogonal to x, just P0x. And when this is not orthogonal, then take another P1 and define the vector field in this way. So this is a section of the vector bundle, y. Then we restrict our moment map to this section. Then the square norm coincides with this one. This is just a calculation. And so our Cartan-Münzner polynomial is expressed by, this is a first term. This is also given by moment map of U1 action related to the complex structure, but we keep it in this way. So second term is important, and the second term is given by the square norm of the moment map along this section. So this is given only by using the spin action of the tangent bundle. Now, of course, we use this vector field, but the right-hand side only depends on x, because if we have x, then yx is determined. So this is a function on the point Rn, R2L. Also, here we use P0 and P1, but this is not, this is freedom. This has freedom. So P0 and P1 can be replaced by any two orthogonal unit elements of V. So we have a space V. Of course, this is a space V spanned by P0 to P1 and Pm. They are orthogonal and orthonormal frame, and so we can choose any P and Q in this space. They are mutually orthogonal and unit. So we can replace P0 and P1 into any P and Q. Yes. And also this section, I told you the tangent bundle, we define some section, and this total set of the section generate a cone, and this is of dimension equal to the base manifold. So this is a half dimension. So I thought first that this cone is Lagrangian, but by a delicate calculation, it is not Lagrangian, I unfortunately. Anyway, along this cone, we have an expression of isoparametric function in terms of the moment map. And yes, so the motivation of this expression is in the work of Shinobu Fujii. He is a PhD student. He was a PhD student of Professor Tamaru. And first, he gave a expression using the Hermitian symmetric space. In this case, the Hermitian symmetric space itself has symplectic structure, so they need not to take tangent bundle. However, usually symmetric space has no symplectic structure, so we need to use the tangent bundle. So this Hermitian symmetric space case was done by Fujii and Tamaru, all the cases. However, these cases, including non-homogeneous cases, I give the expression now. Then there are two cases remaining still. This case was done by Fujii, but in my method, this case is remaining. These two cases are remaining. So how to do this? So these two cases are homogeneous, and homogeneous hypersurfaces in the sphere are given by isotropy orbits of rank 2 symmetric spaces. This is a very old fact. So these two remaining cases are isotropy orbits of these two symmetric spaces, SO5 and SO10 over U5, 5-5 matrix in both cases. So we take the standard basis Eij, which means Ij component, only Ij component is 0, other components are 0, and take the skew basis Gij, and calculate by root system, using root system. And we take the Cartan decomposition of algebra, real algebra, and take the abelian subspace, maximal abelian subalgebra of P. Then we obtain how we express the Cartan-Münzner polynomial in these two cases. As follows. So, using this element of K and define a tangent vector at H, where H belongs to A. So we are considering rank 2 symmetric space. So we have two-dimensional algebra, abelian algebra here. So if we take H here, then we have a orbit of isotropy action of, this is the orbit. This belongs to sphere. This is isometry, so this belongs to, of course, sphere like this. So this is the isoparametric hypersurface. In this case, homogeneous. All homogeneous isoparametric hypersurfaces are given in this way. So we take two-dimensional so rank 2 symmetric space. So here, Euclidean space, maybe K, and so all the orbit pass through this circle point, and then we obtain isoparametric hypersurface. So first, I give a tangent vector here. Here I define YH and extend this YH by adjoint action. Then we have a tangent vector along all the P. So this is a way how to define this vector field Yx. Then along this section again, we have a moment map. This is P is a Euclidean space, so K acts on this Euclidean space, so it can be extended to the action on tangent space. Yes, and this action is a Hamiltonian action, so we can consider the moment map again. And if we restrict to this tangent section, then we have an expression of Cartan-Mencner polynomial in terms of the square norm of the moment map of this isotropy action. This time not spin action, but isotropy action. And this coefficient is given by 3/4 or 3/4, 1. So this is the story of the expression of Cartan-Mencner polynomial in terms of the moment map of the sum group action. And my advantage is that the method is applicable to both non-homogeneous and homogeneous case, unified way, in a unified way. So this is a point of my result. And now I will give some related topics. So the classification is maybe one of goal, but anyway, we can use many part of isoparametric theory to other fields. So, for instance, isoparametric hypersurface in the sphere gives an example of special Lagrangian submanifold of the tangent bundle of one-dimensional higher Euclidean space. This is well known, Javier and Lawson. And also, yesterday Professor Onita told us that the isoparametric hypersurface in the sphere gives an example of compact Lagrangian minimal submanifold of complex hyperquadric through Gauss map. And the volume minimizing property is deeply investigated by Huima and Onita. And also, all isoparametric hypersurfaces have constant principal, constant mean curvature. So this is in some sense give a self-similar solution of mean curvature flow. As I say, isoparametric hypersurfaces develops in this way. So this is a flow. There is a flow, and this flow is in some sense mean curvature flow, and so it gives a self-similar solution of mean curvature flow. This is very interesting, I think. And recently, Zizou-Tan and Yang give an affirmative answer to Yao's conjecture on the first eigenvalue of minimal hypersurfaces in Sn. In all the case of minimal isoparametric hypersurfaces. This conjecture is very famous. So by Takahashi's formula, the eigenvalue may be the dimension of this submanifold is the first eigenvalue. This is still a conjecture, but in all the case of minimal isoparametric hypersurface, Zizou-Tan and Yang gave an affirmative answer. This will be published in Journal of Differential Geometry soon. And homogeneous case has been already proved by Professor Kotani or Professor Muto and Onita too. But non-homogeneous case is very difficult, or we need some other ideas. And Zizou-Tan and Yang gave a very, very, very good idea to obtain this affirmative answer. And also, Zizou-Tan and Chen and Yang obtained that two focal submanifolds or OTF game type isoparametric hypersurfaces give examples of Willmore submanifolds. Willmore submanifold is a generalized notion of Willmore surface. So this is a critical point of certain conformal invariant functional given by mean curvature and some data of isoparametric hypersurfaces. So they show that this gives an example of well-more submanifolds. And also, you know, the chance conjecture. There are many versions of chance conjecture, but one version is that the length of the second fundamental form of a compact minimal submanifold with constant scalar curvature in the sphere take discrete values. This is a chance problem. And some answer is given by Tokarev and Kobayashi and some other people. And on this problem, isoparametric hypersurface has, of course, constant scalar curvature. So we have a test case using, we have a test, we can do test using the isoparametric hypersurfaces to consider this problem. And also, recently, Zijiutan and Xie and Yang, Xie and Yang is a student of Zijiutan, give another result. So using the decomposition of sphere, I told you this part B plus and this part B minus, such decomposition, applying Gromov-Lawson-Shen-Yao gluing method, they give construct compact Riemannian manifold with positive scalar curvature and non-trivial topology. So as I said, we have a decomposition of sphere in maybe, it's difficult to write, but this part B plus and this part is B minus in this way. So we can divide sphere in two parts. And if we glue B plus with B minus, then this is nothing but the original sphere. But if we glue B plus with B plus, this becomes other manifold, not sphere. So, but the gluing is very difficult. So they use the gluing method of Gromov, Lawson, Shen, and Yao, and they obtain such a positive scalar curvature manifold. Also, this is an analysis result obtained by Gu and Xie. Gu is also a student of Zijiutan. And they use isoparametric hypersurfaces to obtain a counterexample to Breiz's problem on the solution of Ginzburg-Landau system. This is a Ginzburg-Landau system. There is some problem, but they could construct counterexamples by using the isoparametric hypersurfaces with 4 and 6 principal curvatures. And this is very interesting. So these are related topics, so I hope you are interested in isoparametric hypersurface theory. Thank you very much.